Alright, everyone. Hello, this is Orion's brightest star, and today we are going to be doing some more differential geometry. Specifically, we are going to study space curves and rigid motions. So, to begin, we're going to be talking a little bit about the cross product. So, here's what we're going to do. We're going to define a vector. And then we're going to define another vector. So if we have these two vectors a and b, we can calculate the cross product a times b, like so. And that is in R3. So this cross product is unique to R3. That is, there does not exist a two-dimensional cross product. And let's take a look at some lemmas that stem from the cross product. So we're not going to prove any of these. I'm just going to write them down. So the first one is the cross product of a and b is orthogonal to a and b. So when I say sine of theta, what I mean is the angle between the two vectors. And interestingly enough, the magnitude of the cross product corresponds to the area of the parallelogram, which is spanned by the two vectors. So this is the area. So if you've taken physics before, you might be familiar with the right-hand rule, but the right-hand rule is simply so. This is a very badly drawn hand, but if the index finger points in the direction of A and the middle finger points in the direction of B, then the thumb, if you stick it perpendicular to both of them, is in the direction of A times B. Additionally, we have that A times B is the negative of B times A. Furthermore, we have that if we have some scalars, lambda and mu, then this expression becomes and it's basically um, the same for the second argument, so I'm not going to write that down. So the last thing we have is, you can think of it as a sort of another product rule. So if we have the derivative of the cross product of two curves, space curves, gamma and beta, let me write down gamma and beta, are functions from an interval I to R3, then the derivative is equal to gamma prime times beta plus gamma times beta prime. And remember, the cross product is not commutative, so in fact it is anti-commutative, so you cannot swap the orders of the two curves. So that's a bit of background knowledge on the cross product. So let's move to a proposition. So if we have a space curve gamma I to R3, then the curvature is equal to this. So let's prove it. We already know that the curvature is equal to the perpendicular component of the acceleration divided by velocity squared. That stems from the previous video. So you can think of this as sort of a sine theta over v squared, where if we draw a diagram, if this is v and this is a, this is the perpendicular component of a, because that's a right angle. This will be theta, and this is... So you can see how the perpendicular component of acceleration is equal to the magnitude of a times sine theta. And this becomes, if we multiply the numerator and denominator by the magnitude of v, then we get that. And this is the formula for the magnitude of the cross product. So v times a over v cubed. So now we can define, I believe it's called the Frenet frame. Correct me if I'm wrong. I might not be, I learned this from a book, so I might be messing up the pronunciation, but it is simply the basis comprised of the unit tangent, the unit normal, and what is called the unit binormal, which is the b. So let's define them. We're already familiar with the first two, so this should be review. And then the unit binormal is simply the cross product of the unit tangent and the unit normal. So let's say we have a curve going this way. This is our unit tangent. Our unit normal, I believe, should be going this way, and the binormal should be pointing down, and they're all at right angles to each other, so something like that. It's pretty, badly drawn, but hopefully that should shed some light on that. We can also define something called the torsion. So torsion. And it is essentially the negative of the derivative of the binormal and the normal over the magnitude of v. So just like curvature, we also want torsion to be independent of parametrization. So let's prove this. Oh, also, by the way, this negative sign might not exist in other videos or books. As I mentioned in the very first video, I'm using TAP to go over this content, and TAP uses the negative sign for torsion, so keep that in mind. So let's say that we have reparametrization of the curve, and we'll denote it with a tilde. So we have the unit tangent, which is that, the unit normal, which is that, and the binormal, which is that. So our modified, quote-unquote modified torsion should be the derivative of that, normal, over, and if we take a look at this, we can use the chain rule because we have this. So we have a regular binormal prime of phi of t times phi prime of t. That's the chain rule. And then we have that, since we have this formula. And if you haven't watched the video on reparametrizations, you really should before watching this, because if you haven't, this might make no sense to you. We've seen before that velocity transforms like so. And this allows us to cancel out these phi prime. So we end up getting a formula that looks a little something like this, which is just the torsion of phi of t. Therefore, torsion is independent of a parametrization. So now let's take a look at another proposition. if we have a space curve, the trace of gamma is constrained to a plane if and only if, we can also use this symbol, the torsion equals 0 for all t in I. Now, the proof of this is pretty long. I'm pretty sure I did an exercise like this in Do Carmo, but I'm not quite sure. But I won't be going over it. Instead, I'll be moving to the Finite equations. And they look something like this. You can calculate them yourself. I don't think it's very difficult to, but the derivative of the unit tangent is equal to the magnitude of the velocity times curvature in the direction of the unit normal. The derivative of the unit normal is equal to the negative of the magnitude of velocity times curvature in the direction of the unit tangent plus velocity torsion binormal. And the derivative of the binormal is negative velocity torsion normal. So these are very important equations in the study of differential geometry of curves. So you should know these. These are pretty important. So now let's move to a second topic of this video, which is on rigid motions. So rigid motion. And a rigid motion of Rn, it can be 2, 3, whatever, is a function f from Rn to Rn that preserves distances. So the distance from f of p to f of q is going to be the distance of p and q for all p and q in Rn. Furthermore, we can say a matrix A is orthogonal if we have that the rigid motion associated with the matrix of P is equal, the norm of such is equal to the norm of P. So what that means is if we have a matrix A it sends vectors on a sphere to the same sphere. So this is the rigid motion. And this implies A is orthogonal. So let's look at a proposition. These are equivalent, so equivalent. That means if one is true, all of them are true. So the first one, that is a rigid motion. The matrix A is orthogonal. the inner product, that should be inner product. So if we have an orthonormal basis, then the rigid motion keeps it as an orthonormal basis. The columns of A form an orthonormal basis of Rn, and so what this basically means is this is called the transpose, and it's basically when you swap the rows and columns. So if we have 1, 2, 3, 4, then a transpose equals something like this. This is called the identity, and that's basically just where the diagonal is 0 and everything else, diagonal is 1, what am I saying? And everything else is 0. So that's a lot. So I guess let's prove it. So we prove this in segments. So first we prove that 1 is equivalent to 2. So if LA is a rigid motion, then we have that so this simple statement simply just proves that A is orthogonal by the definition of an orthogonal matrix, if we recall that. Conversely, we have that and because A is a matrix and therefore the rigid motion is linear, we can do that, and we already know from the definition of an orthogonal matrix that that is equal to that. So, because of this, LA is a rigid motion, because this represents the distance between LAP and LAQ, and this represents the distance between P and Q. Okay, now let's prove 2 is equivalent to 3. So let's assume 3 is true. So we have this. Then we can calculate the norm. Remember, by the definition of the norm and its relationship to the inner product, we have and this stems from 3, and that's just the definition of the norm. So there's that. And then for the converse, if we have this from the relationship between the norm and the inner product, and this becomes So when you solve, this becomes the norm of p squared and the norm of q squared. If we solve for this, we end up getting, and I'm not going to do all the algebra, but it ends up being something along the lines of this. And therefore, if the rigid motion preserves norms, because the inner product depends on the norm, then it must depend on the, then it must preserve the inner product as well. Now let's prove if 3 is true, then 4 must be true. This is pretty obvious because if we have two vectors whose inner product is 1, then the rigid motion is going to be 1 as well. And if their inner product is 0, then their inner product of the rigid motions will be 0 as well. And therefore, it preserves orthonormal bases. I know there's like memes about how textbooks are always like, things are obvious, but I think this is fair to call obvious. Now let's prove 4 implies 5. So if LA preserves orthonormal bases, then the columns form an orthonormal basis of Rn. If you know a little bit of linear algebra, this might be clear, but it might require further explanation if you haven't. The columns of A end up being and the reason why is because when we write vectors like this is basically just saying E1. If we write this is basically saying E2, and so on. So if we do matrix multiplication, I don't know whatever this is. If we look at E1, this is LA, this is E1, we end up getting, the elements in this first column, whatever they are. So that's basically a very quick and dirty explanation of why this is a one-liner. Now let's show that 5 and 6 are equivalent. And then after that, we're going to go back and show that 5 implies 3. So what we're saying here is that the columns form an orthonormal basis of Rn. That implies that the transpose times the matrix is equal to the identity. So what happens if we have the ijth term of the A transpose times A? That is equivalent to the inner product of rho I of A transpose with column J of A by the definition of matrix multiplication. And because the transpose is a transpose, that would be column I of A and the column J of A. And since A forms an orthonormal basis of Rn, it's pretty clear that this is our old friend, the Kronecker delta function, which I covered in the first video. I don't even know if Tap covers Kronecker delta. He hasn't yet, but let's prove that if the columns of A form an orthonormal basis, then this formula holds. So if we have this, that is equal to of the sum from L equals 1 to N, let's call it PL, EL, and then sum of S equals 1 to N of QS, ES. And that is going to be equal to the sum of, the double sum actually, of PLQS and remember, because this is going to be orthonormal, so this is going to be 0 if EL and ES are different. So, and therefore if L and S are different. So we're going to have P1, Q1, 1 is the same as 1, plus all the way to Pn, Qn, and that is the inner product. So that concludes the very long proof. So let's look at let's look at this proposition. I'm not going to prove it, even though it's short, but I think it's useful to know. So if F is a rigid motion of Rn, then F equals the translation by a vector Q composed with LA for a unique choice of Q in Rn and the matrix A in On, which is the set of n by n orthogonal matrices. Furthermore, if we have a matrix A that is orthogonal, then the determinant of A will either be positive or negative 1. So, the reason why is because we know from before that the transpose times A is going to be equal to the identity. So 1 is equal to the determinant of I. If you haven't seen the determinant before, you're kind of just going to have to trust me on this one, but if you do know about the determinant, you can follow through this. So we have that, and we can actually split them up into two, like so. And the transpose is equal to, the determinant of the transpose is equal to the determinant of the regular matrix. So we have that. So therefore, the determinant is going to be either 1 or negative 1. So we call the matrix, or the rigid motion, proper if, so for the rigid motion, F equals translation times, or composed with LA, and it is improper if the determinant is equal to -1. And what's an example of an improper rigid motion? What if we have reflection? Let's try. Can I lower it? Okay, that looks pretty cool. So if we have a reflection across a plane, that is an improper rigid motion. And the reason why is because you cannot turn this into that, like, physically. Like, if you imagine, like, I don't know, if you imagine, like, a iPad or whatever, that's what I'm using to get away. If I hold up an iPad to, like, a mirror, I can't, like, turn it into its reflection because, well, in this case, I kind of can, but usually I won't be able to. So, furthermore, we can say an orthonormal basis is positively oriented if the orthogonal matrix whose columns are the basis in that order, the determinant would be 1, and it would be negatively oriented if it has determinant -1. So for the last thing I'm going to do, I'm going to share with you a theorem. And it is one of the fundamental theorems of plane and space curves. So if we have some function, kappa s, from I to R, this backwards looking E means there exists a unit speed plane curve gamma whose signed curvature is kappa s. And if we have, actually that's not it. We have two curves, then there's a and these curves have the same signed curvature, then there must exist a rigid motion, a proper rigid motion, in fact, which we'll call F, such that gamma hat equals F composed with gamma. So I'll prove, well, the first part um, you can do pretty easily. Let me show you. First, we define the angle function as kappa S u du plus, I don't know, let's call it 0 for now. So remember that sine curvature would be the derivative of the angle function. So we can just define it like so. Then define velocity as cosine of theta sine theta. Then we can define gamma as this, the integral and we've done it. We've defined a curve such that it has the sine curvature function supposed above. So that's basically all I have for today. And as always, thank you for listening, and I'll see you in the next video.